In this video, we're going to be learning about an important concept in acid-base equilibria that can not just help our understanding of pH indicators, but also other applications of acid-base equilibrium. We start by considering this hypothetical pH indicator and its ionization reaction. We can write the Ka for this, which looks like the Ka of any other acid ionization, where we have concentration of the base form of the indicator times the concentration of H3O+ divided by the concentration of the acid form of the indicator. In the previous video, we talked about how we can shift the equilibrium justified by Le Chatelier's principle simply by changing the amount of H3O+ or OH- that are present. For example, if we add acid, that means that we are increasing the concentration of H3O+, meaning that we are increasing the reverse rate of our reaction, and therefore that will cause an increase in the amount of the acid form of the indicator. However, if we were to add OH- instead, the OH- would react with the H3O+ in solution and neutralize it in order to make water. Because we have less H3O+, because of this neutralization, that means that the concentration of H3O+ would decrease, meaning that our reverse reaction rate is now slower than the forward rate, causing the equilibrium to shift to the products and therefore increasing the amount of the base form of the indicator that we have. Now, eventually, if we play around with the concentrations of H3O+ and OH- in solution, where we can add just the right amount of acid or base to cause an interesting phenomenon to happen, where the concentration of the acid form of the indicator and the concentration of the base form are exactly equal. Now, for every pH indicator, this is different, but the phenomenon that explains why this occurs is fundamentally the same. When we get to this point where the acid and base forms of the indicator are identical, this is what we call the transition point. And transition points are very important for understanding acid-base chemistry. Now, if the acid and base forms of the indicator exist in equal concentration, something very interesting happens to Ka. So at this time, if we consider our Ka formula, that means if the concentration of the acid and base forms of the indicator are equal, that means because we have the concentration of the base form divided by the concentration of the acid form, if they are equal, that means that these two can cancel each other out, meaning that Ka at this one point is equal to the concentration of H3O+. Now, this is a very useful simplification that we can make, because if we take the negative log of both sides, well, we know that the negative log of the concentration of H3O+ is simply equal to pH, and pH is something very useful that we can measure. Now, if we take the negative log of Ka, which seems like a gibberish thing to do, we end up with a measurement that we call pKa. pKa is just simply the negative log of Ka, in the same way that pH is the negative log of the concentration of H3O+. What isn't important is so much what pKa is, so much as how we can find it. Let's say that this hypothetical indicator solution is made up of an indicator that actually has two different colors. Let's say that in its acid form, our indicator is red, and let's say in the base form, our indicator is yellow. Well, if we have an equal amount of red as we do yellow, when our indicator falls to the transition point, our solution is not going to appear red or yellow, but orange. Now, the fact that we can identify the transition point so easily just by looking at the indicator visually means that we can determine that this specific pH, where the concentration of acid and base forms of the indicators are equal, corresponds to a specific color point, that allows us to experimentally determine the transition point of an indicator simply by looking at it. So, in short, the definition of an indicator's transition point, which is also known by the term endpoint, because whenever an indicator changes color, this is a signal to end a titration reaction, of which indicators are normally used. So the definition of an indicator's transition point is the specific pH at which the indicator begins to change color. So the idea in this hypothetical indicator is if the concentration of the acid form is greater than the concentration of base form, our solution will be red. But if the opposite is true, if the concentration of base form is greater than the concentration of the acid form, the indicator will be yellow. But right at this transition point where we have equal concentrations of both forms, the indicator will have an equal amount of both forms and therefore will be a mixture of the two different colors. And this allows us to do some relatively simple calculations involving transition points and pH indicators. For example, this indicator has one of the most radical color changes that exists, bromocresol purple, which is yellow if the pH is below 5.2 and light pink at a pH of greater than 6.8. So we can use this in order to determine the Ka of bromocresol purple by considering its transition point. So if we know that the color change of yellow occurs definitely below a pH of 5.2 and pink at definitely greater than a pH of 6.8, we can simply take the midpoint of these two pHs here, which comes out to being exactly 6.0. So this is the pH at the transition point. And since we know the transition point is where the concentration of the acid form, which is again the yellow form of the indicator, is equal to the concentration of the base form, which is the pink form of the indicator, this is the point at which pH is equal to pKa. So if we know that 6.0 is the pH at our transition point, that must mean that the pKa must also be equal to 6, and all that we need to do to find Ka is take 10 to the negative pKa in order to find that out, and therefore we have found out that the Ka of bromocresol purple is approximately equal to 1.0 times 10 to the negative 6, which is a definite number that we can conclude. So again, what this indicator shows us here is that a pH of approximately 6, because this is a range of color change here, is the point at which the acid and base forms of the indicator will be equal in concentration. We can also use pKa and the concept of transition point to predict what the color of a specific indicator is going to be under specific conditions. So alizarin yellow is this indicator here, which is an indicator that changes from yellow in its acid form to red in its base form. But we see that we have a very high pKa here of 11.0. So what this means, remember that pH is equal to pKa at the transition point. So what this means is that our color change occurs at a pH of approximately 11, meaning that at a pH, if the pH is greater than 11, that means that our solution is going to be red, and if the pH is less than 11, that means that our indicator is going to be yellow in color. So what we need to do is simply figure out what the pH of this hypothetical solution is going to be, in which the concentration of OH minus is equal to 1.0 times 10 to the negative 5 moles per liter. Well, we can do this by simply taking the negative log of the concentration of OH minus, which we can do in our head here. We can see that this is 5. The problem is that this is the pOH, meaning that in order to find the pH, we need to simply take 14 minus the pOH, so 14 minus 5 is a pH of 9. We can clearly see that 9 is less than 11 here, meaning that the pH of 9 is less than the pKa of our acid, which again, pKa being equal to pH is where the concentration of the acid and base forms are equal. So because the pH is less than our pKa, that means that our indicator is going to be in its acid form, and therefore our solution is going to be yellow. In the next video, we'll look at the most interesting application of indicators, that being how to use indicators not just to identify whether the pH of a solution is above or below a specific point, the transition point, but actually use them to determine the specific numerical pH of an acid-base solution.